So today we're going to go ahead and talk about centripetal forces. So first thing I want to look at, so let's say we have a ball and a tube, just like this example above. So earlier last week we talked about okay, what direction would that ball go, A, B, or C, if the wall of the tube was removed? And we said, oh, it's going to go C, and that represents the tangential velocity. And the reason it's going to go C is because there's no force of the wall pushing it inwards to keep it moving. So when we think about forces, so in what direction does the net force of an object need to be to keep an object in circular motion? The net force needs to be pointing inwards. So the F net needs to be pointing inwards on this object so that it keeps moving in a circle. And I think of it, when this ball is in here, there is the normal force pushing it inwards to keep it moving in a circle. So net force to keep an object moving in a circle is going to be needing to point inwards, which I think inwards, again, that is centripetal or center seeking. Cool. So let's think of another example. So if you're going to round a corner quickly while driving on ice, what is going to happen? It's really hard to turn while you're driving on ice because there's not much friction between you and the ground, while on a normal road, there is way more friction. So friction is actually one of those things that helps keep you moving in a circle. So there is, depending on so many different circumstances, different forces will help you move in a circle. So let's say you have, for example, 3A, you have a mass connected to a string, and it's moving in a circle. So the centripetal force, which we'll talk more about in a second, is just going to be provided by the string or tension force pulling it inwards. Or you have a car on a corner of a highway. Again, friction keeps things moving in a circle when we're talking about, cars driving on the road. Let's see, moon orbiting the Earth. So let's say we have the Earth right here and we have the moon, and the moon is orbiting aroundwards. The centripetal force, or the force pulling it inwards, is going to be the force of gravity. Okay, so we're going to chat about a couple more things now. So we're going to talk about this word centripetal force. So what I want to clarify, so centripetal force is just basically a fancy word for net force directed towards the center of a circle. So again, just fancy word for net force for circular motion. It is not, everyone always thinks centripetal force is an additional force. It is not an additional force. It is just the sum or the combination of forces that make an object move in a circle. One little notation, different people might say different things, but this is what I always do. When I solve circular motion problems, I say that towards the center of the circle is considered the positive direction. Cool. So a couple things to keep in mind. One other thing, this word centrifugal force comes up a lot. And people are like, oh, the centrifugal force makes you go outwards or feel like you're going outwards. The centrifugal force does make you feel like you're going outwards. This is just a perceived force that you happen to feel because you're in an accelerating frame of reference while you're moving in a circle. So this is not a real force. It's not a real force that we can say oh, that's the tension, whatever. It is just how you feel. So don't use this word centrifugal force. Again, you can use it, but it is not, when we deal with circular motion problems, it is not what causes things to happen. It's just how you feel. Cool. So we're going to go ahead and draw some free body diagrams and then set up an equation representing the centrifugal force. So I'm going to go ahead for each of these pictures, and I encourage you to do it yourself first and then check back into the video. I'm going to draw a free body diagram. So I have FG right here. I have force of tension right here. This picture, I have normal force going up. I have force of gravity going down. Tension pulling to the left. This one right here, there's no friction on this one, so I have tension right here. And FG right here. Cool. So now let's go ahead and set up an equation representing the centripetal force. So in this picture, it is moving in a circle in that vertical direction. So we know towards the center of the circle, this is the center right here, is a positive direction. So we're going to say for this one, F net C is going to be equal to our tension force minus force of gravity. And again, F net C represents the centripetal force. Cool, let's try another one. So for the next one, it's moving on a horizontal surface. So it's moving I can't draw my perspective quite right, but something like that, horizontal circle. So the only forces in the horizontal direction are just tension. And we'll say that to the left is the positive direction because that's where the center of the circle is. So if we set up F net C, it is just going to be tension. And again, for this one, I think of like, for this example, we're looking at the x direction for the F net C, and for the other example, we're looking at y direction. Oftentimes problems we do, the object will only be moving in a circle in just the x or just the y direction, which makes our life easier. Cool, let's look at this one. So rock is moving towards you in a horizontal circle. So they already drew the circle. Gosh, it's great when they draw the circle for me. So we're dealing, the circle is in the x direction. So that's the F net C we're going to deal with. So FG looks like that is perpendicular to F to the x direction. So we're not even going to worry about that. Tension itself, though, that's pointing in both the x and the y. So just like we had so much practice earlier in this year, we're going to split tension into our x part and our y part. And then when we go ahead and set up, and again, we'll say to the left is the positive direction because center of circle is right here. F net x is just going to be tension x. Cool. We got all these lovely things. Thanks for watching. Oh, no, we're not quite done. We're going to do one practice problem together, and then you'll be here. Okay, so let's go ahead and look at this. So let's go ahead and read the problem and draw our free body diagram. I went ahead and wrote the steps on the right. So we have a box of mass M. Here's the box right there. I'll highlight it in yellow. It is held, okay, so it's held in place by friction. It rides on the flatbed of a truck while traveling at a constant speed v. The truck is on an unbanked circular roadway having a radius of curvature r. Okay, so this little line right here, that's not a rope, even though it looks like a rope. That's just like saying what the radius is. Okay, so for A, on the diagram above, indicate and clearly label all the force vectors acting on the box. Oh, draw a free body diagram. I love drawing a free body diagram. So try yourself and then check back in. So for this object, we always have gravity act on things. So gravity is going to be straight down. So we have a surface pushing up on that block. The flatbed of the truck is pushing up on the block. That is the normal force. So now let's think about what direction friction is going to be. Okay, so the object wants to go just straight this way. That is its tangential velocity. That's direction it would want to go. Sorry, I lied. If we're thinking about, if I think of the car, okay, the truck is moving clockwise, so the object would actually want to slide back the opposite direction, but tangentially either way. So friction is just basically going to push it inwards, and we are dealing with, if it's not moving at all, because this little object right here in yellow is not moving on the truck, we're dealing with static friction. So it's like it wants to move, and friction is pushing it back inwards, perpendicular to it. So we'll say force of static friction is just pointing inwards to keep it moving in a circle. Cool. So now let's go ahead and do B. So what condition must be satisfied by the coefficient of static friction mu k between a box and truck bed? Okay, so we basically want to find the coefficient of static friction. So friction is, let's do our coordinate system. So we have y direction, we're just dealing with Fn and Fg. X direction is going to be towards the center of the circle, a horizontal direction. We just have one force there, and we'll say towards the center of the circle is positive. So we are dealing with x direction. And again, that is the direction it's moving in a circle. So let's go ahead and set up F net C. So F net C equals, let's see, the forces in the x direction, which is just force of static friction. Okay, F net C is MAC, and I did not clarify that in the last thing. F net C is just your mass times your centripetal acceleration. Force of static friction is going to be mu times Fn. Cool. Okay, so we know, let's see what we know. AC is just going to be b squared over r equals mu. Fn is not allowed in our answer, so let's see if we can figure out Fn. Let's go ahead and go to the y direction and just set that up. So F net y equals, we have Fn going upwards and Fg going downwards. F net y, F net is always ma. We're not dealing with AC now because we are dealing with the y direction where it is not accelerating or moving in a direction of a circle. So we have what? Fn minus Fg is going to be big M little g. Acceleration is 0, so it's not accelerating. So it's what? M times 0 equals Fn minus mg. So Fn is just equal to mg. Cool. Makes sense. So this is, and I should be careful using big M for this. I was getting lazy. Big MG. Cool. M's cancel out. Okay, and we are solving for mu. So then we have what? B squared over R equals mu G. Let's go ahead and divide both sides by G. So it's like multiplying by 1 over G. So V squared over GR is going to be mu. Cool, we got our final answer. Cool, so I'm going to go ahead and just draw a couple more free body diagrams. If you want a little more practice, another minute or two, I'll go ahead and put that below, but otherwise feel free to watch. So we're going to go ahead and just set up FNetC for a couple more free body diagrams, which is always good practice. So let's draw a free body diagram for each of them, try it yourself, and then check back in on the video. So let's see, for this one we have force of gravity, we have tension. For this one we have Fg, we have tension. For this one we have gravity always downwards, the rope is pulling it back downwards. Cool. Great, so now let's go ahead and look at each one. So this one, it's swinging a rope, kind of a circle, like a vertical circle like that. Towards the center of the circle is going to be what? That direction right there. Cool, so in this case, that's the center of the circle. So we'll say that's like essentially the direction we're worrying about. FG, we'd have to split that into your, let's call this like the Y direction and the X direction, and that'll be some angle theta. So in this case, we could say FNetC equals tension minus FGY if we just say that, you know, this direction right here is our Y direction. Cool, let's look at one more. So it's moving in a vertical circle, so something like this, with the string horizontal. So this one we could say, let's see, to the left center is the positive direction. FNetC is just going to be equal to tension. FG is perpendicular to that, and at that point, yeah, cool, just tension going inwards. Let's look at this one. Oh man, another vertical circle. So again, we're looking at Y direction for FNetC. Center of the circle is right here. So downwards direction is positive. My circle doesn't really show that, but sorry about that. So again, towards the center of the circle is positive. So in this case, downwards direction is positive. So we can say FNetC equals FG plus tension. Cool, and we got it. Thanks for watching.